Welcome back to another practical session. This particular video is on parallel circuits. So what we're going to have a look at, we're going to go back through the objectives on this one. We're going to see in a parallel circuit that the voltage, supply voltage is equal to voltage across one branch is the same voltage across the second branch, the same voltage across the third branch. That the current in the parallel circuit, the current through one branch plus the current through the second branch plus the current through the third branch is equal to the supply current. And the resistance obviously is the three resistors are inversely proportional to the total resistance. 1 on equivalent resistance equal to 1 on R1 plus 1 on R2 plus 1 on R3. It's very important before you do this particular practical exercise that you understand the theory content, where it comes from, and the simple way of doing that obviously is to remember Kirchhoff's current law, KIL. Nice easy one to remember, that the sum of the currents entering a junction is equal to the sum exiting the junction. Okay, so the particular experiment here, we're going to have a look at two resistors, two 150 ohms, purely due to the ease of calculation. So we'll flip that over. So I'm going to connect up two 150 ohm resistors in parallel and measure the total resistance. So as our formula gives us, so one resistor connects to that one, and the other resistor connects to that one. So these two resistors are in parallel with each other. So I'll plug the meter in, and as we've discussed previously, I'll put it on ohms, and I'll null the meter out, plug them in, press the null button, we'll get 0 ohms. Before we do that, let's do the theory calculation behind that. What is two 150 ohm resistors in parallel going to give us? It's going to give us half the resistance of the one of them. Okay, remember the total resistance is going to be equal to less than the lowest value resistor, because both resistors are the same, they're both 150. Okay, so 1 on RT, 1 on total resistance is equal to 1 on R1 plus 1 on R2, which is equal to 1 on 150 plus 1 on 150 is equal to 1 on RT. Working that through on the calculator, and depending on who your facilitator is, they'll give you different methods of doing this. But simply we go 1 on 150 inverse plus 150 inverse, so 1 on plus 1 on, equals that answer there. Inverse that answer, 1 on RT, is equal to calculation, so that is equal to RT is equal to 75 ohms. Hence both resistors are the same, half the value of that one resistor, in this particular case 75. Let's have a look. So we'll plug the meter in, and what do we measure? 75.3 ohms. There you go, that works quite well. Okay, let's wire that one up. We'll just keep with the two resistors here. So we'll wire this up as per the circuit diagram. So I've got the power supply into the switch, out of the switch, into the ammeter, into the positive of the ammeter, out of the ammeter. I'll just unplug this multimeter from this so we just don't confuse the circuit. Okay, these are my two resistors in parallel, so I was to do it the same way as the picture, so the resistors are going that way, like that. Okay, so we can plug the ammeter into this parallel branch here. So we'll plug it into that one there, which is the same as the ammeter plug into there, which is that resistor there. Remember, they're both 150 ohm. And the secondary, this one here, which is that point there, plugs back to home. This point here plugs back to home. So we can see voltage is connected via the ammeter, or the current flow through that. It comes into the parallel branch, so the current will be distributed through that resistor and through that resistor. Those two currents, okay, through these will add up to be the supply current, which is there. Let's have a look at that theory. Okay, so the voltage we're going to use in this particular case will be 15 volts. So the applied voltage will be 15. So 15 volts. So 15 volts. Now, I is equal to V on R. So I is equal to V on R. We hold over I V on R, which is equal to 15 volts divided by the total resistance, which is 75 ohms, is equal to 15 divided by 75 equals 0.2 of an amp, 0.2 of an amp, or 200 milliamps. Let's have a look and see if that is the case. We'll put the ammeter on. We've got to put the voltmeter in as per circuit. The voltmeter says go across the supply. Voltmeter, go across the supply. So we can do that, and I'll put it up here. Got a nice view of that. And the voltmeter goes across the supply. So I'm going to turn the voltage down, turn the switch off, turn this on, just to do 15 volts. And the theory tells us that we should have 0.2 of an amp flowing through total current. This is total current, remember? Total current flowing through the circuit. That's probably not this particular circuit diagram here is what we're looking at. Sorry, so the total current flowing through that circuit. 0.2. Turn it on. So probably it's a little bit difficult to see through all these leads, but we've got 0.2 of an amp flowing total current. There's 15 volts flowing through that circuit. 0.2. Good. Total current. So IT is equal to 0.2 of an amp. Now the next thing we're going to do is see what Kirchhoff's current law tells us, that this current plus this current is equal to the supply current. So we'll have a look at working out the current through the first resistor and the current through the second resistor. IR1 is equal to this one, call this one R1 and this one R2. Turn the power off. Remembering before we only use 1 lead for an M meter. Now what I like to do when measuring currents on parallel circuits, I'd like to put the M meter at the bottom of the resistor, not at the top, so I can see the current flowing through the resistor, then into the M meter. So having said that, we'll make this one R1, which is this one here, unplug the resistor. Plug the M meter into the resistor, so it's flowing through, and then whatever lead was plugged into it, plug that back into the meter. So plug that into there. So then we can turn that back on, and we've got 0.99, almost, I'm going to call it 0.1 of an amp. So IR1 is equal to 0.1 of an amp. For those of you who are starting to think, it's probably pretty true that both resistors being the same value should have the same amount of current. That's valid. So we'll turn that off. And this one's my second resistor. So unplug at the end of it, so it's got to go through the resistor. Current goes into the M meter. Whatever lead was plugged into that plugs back into the M meter. So it's flowing through, measuring that current. Turn it back on. Still got 15 volts and 0.1 of an amp again. So 0.1 of an amp. So IR2 is 0.1 of an amp. Therefore, we can say IT is equal to I1 or IR1 plus I2, which is equal to 0.1 plus 0.1, which is equal to 0.2 amps. Which is exactly the same as the total current, which we calculated before. So there we go, I1 plus I2. Excellent. Turn that off. Now the last part of this practical experiment was to confirm that the same voltage existed across each resistor in a parallel circuit. So what voltage we measure here, it's the same voltage here and here, which obviously is apparent in a lot of electrical industry today. Obviously power points and lights wide in parallel. What we'll do is we'll just unplug this M meter. like so. We'll keep the voltmeter in play as we've got it here. We'll grab another lead for the, change this here to be a voltmeter, so I'll take it out of the amps and plug it into volts. Put on volts, DC. Okay, once again, we can measure voltage while the circuit's on. Okay, I'll turn it on. So I'm going to measure the voltage across this resistor here. So this is, say, well, that was R1, that's R2. So VT, total supply voltage, is equal to VR1, which is equal to VR2, and so on and so forth. So VT, 15 volts there, 15 volts, is equal to this VR1, this one here, 15.1, it's 15.1, 15.1, 15, and then we'll unplug that, and we'll measure across this resistor here. We've got 15.09, or almost 15.1, 15.1. So therefore that confirms that part of our theory as well. The same voltage exists across a parallel circuit, the currents add up to equal the total supply current. And therefore that concludes our practical experiment, parallel circuit.